Hello and welcome to my final presentation. My project was inverse design of 3D fabrical metamaterials. My name is Andres Valdiviezo and I worked alongside my professor, Professor Wong. I am currently a student at the University of Texas at Austin. My professor, Professor Wong, he's a professor at Texas A&M University. My two mentors, Sam and Tayson, they're graduate students at Texas A&M. I received sponsorship from the Center for Research Excellence on Dynamically Deformed Materials, also known as CREDS, and this work was supported by the Department of Energy, National Nuclear Security Administration under award number DENA 0003857. So for my project, I worked on a MATLAB inverse design code. And the two images in this slide are part of the code, or basically the results that I gathered from the actual code that I ran. The code itself was called Top 200 EM, and it's basically a MATLAB code of 200 lines that is able to create a 2D structure from the given inputs that basically allows light from the bottom of the image to travel up to a certain point in the XY direction in the image that's listed on the right side. And so the blue image, you can kind of see that there's light traveling to it, and that's exactly the spot that we want to point the light to. And so the structure, the black structure, that's a 2D structure that was created throughout the whole code. And so essentially the 200 lines are done in a specific way using finite element method in order to be able to create this structure and give the correct structure that we want in order to point the light at the right point. This image right here is a more in-depth example of basically what the code does. On the left-hand side, you have the structure created by the code that basically gives us the light pointed exactly where we want it to be. On the right side, where the blue image is, that's where we want the light to be, which is around 200 in the X direction and 100 in the Y direction. And so, yeah, that's essentially what we wanted with the inputs that we gave the code, and that's the structure that it created with those inputs. And so this code is very useful because this kind of application is used throughout many different industries, and so it's something that is very useful to us right now. Now, as for my main goal of this project is to figure out a way to turn this 2D code into 3 dimensions. And as you can see the image here, that's the structure that I showed in the previous slide. That's 2 dimensions. Okay, so the black structure that's in 2 dimensions. And I have to figure out a way to turn this code into the Z direction, which is pointed towards the page, and be able to perform the same equations, the same finite element method, the same analysis using only the code that I was given. And so, yeah, a lot of research had to be done in order to perform this task. But yeah, that's essentially the goal that I need to meet. And in this image right here, that's where I'm showing how it's supposed to look like when I get the final product, and that's where I go from. Now, in order to be able to accomplish the task of turning the 2D code into 3D, I needed to have a really, really good understanding of what the initial 200 lines of the code did. And so I had to individually dissect the whole code and all the matrices and all the different commands and functions in there in order to really deeply understand what's going on in the code, so that way when it comes to changing and modifying the code into my own words, I'm able to do it more efficiently. And so in these 3 images, I'm basically just showing a few of the matrices that were in there and what they're doing and how they relate to each other, and how I would essentially have to turn this into 3D, or what it should probably look like once I'm able to figure out the different partial differential equations that I need. One of the biggest parts or chunks of the code was the finite element method. And so this code took about maybe 80 lines, and those 80 lines had to do with this right here. So this process of finite element method basically works like that. I mean, you have a domain, which is, in my case, was a huge 200 by 400 matrix, and this matrix was then split into different elements. Those elements were then split apart and were computed differently with the certain equations, the different partial equations that I'm trying to solve for. And then from those elements, everything's put back together, and then it spits out exactly what I wanted to have, which in my case would be the lights that was being pointed in the specific location that I wanted it in, and also the specific structure that I wanted to have at the end. So that's what the process was doing in the finite element method that I needed. In addition, one huge complication that I encountered was that the code itself, the 200 lines that I was given, they performed the finite element method, but they performed it in 2D, obviously, because it's a 2D dimension code. However, the issue with that is that the code itself um, basically hard codes the finite element line by line, and it does it in a 2D, in a 2D dimension. So the issue with that is that most people, what they usually do is they use the MATLAB in functions, the functions that are already in MATLAB in order to perform the finite element method. However, in this case, since everything was coded line by line, then I had to figure out a way how to even code this in the first place, how to turn 2D into 3D. So that took a lot more research and a lot more time. And in this image that I'm showing here, that's actually a paper that I was able to find that kind of give me a sense of what 3D finite element method in MATLAB is supposed to look like. But the big issue with that is that this code itself was for statics, for mechanics, for those kind of applications, which was not very helpful in my case, which I'm just studying photonics. This is what I'm doing right now, and so it was difficult to find a way. In this slide right here, I'm showing a part of a code that I kind of got inspiration from, and I wanted to apply it into my own code, but I had issues with it too because of the different applications that this paper was from. The applications were very different, and I struggled a lot with trying to bring it into my own code, but I did get some results from that, but it was not to what I needed it to be. And so at the end of the day, it was not too useful to get inspiration from other pieces of code. And yeah, I just rather just work on it on my own without getting really help from other pieces of code because they were not very helpful to me at the end. For my last slide here, I'm showing one of the resources that I was looking into. And it was actually a book that was cited in the code that is the way that the author of the code designed the 2D finite element method. And within that book, there was a three-dimensional explanation of how things are done. However, I needed more experience in of finite element method because prior to this, I had no experience whatsoever with it. And so what I had to do is I had to replicate my results in one dimension and then in two dimensions. And those are the other two images that I'm showing here. Those are handwritten notes of me trying to replicate the results and trying to do the finite element method by hand in order to be able to transfer over that to 3D. And yeah, that's where I stayed for the remaining 2 weeks. I was trying to figure out a way on doing the 3D finite element method, but everything I tried was not working, and so I just kept running into issues, and those could have been solved with more research and more experience, but at the time I just didn't have that, and so yeah, I really tried my best with that. Um, I really did my research, and I wish I could do more, but yeah, that's where I stayed so far, and All right. Yeah, so that's my presentation. Thank you.